All right. So in our meeting on Tuesday, we opened with this idea of training a machine learning model, looking at the results, and finding that they're not good enough. And we said that there are many things you might potentially want to try and do in order to improve your results. You might try and correct a problem with the data, for example, a data leakage issue or a problem with some of the features or labels. You might try to find and correct a problem with the way the model was trained. You might use a more complicated model, a less complicated model. You might need to try and get more samples for training. You might try and get data in order to add features to each sample. Or you might add more features using transform versions like nonlinear transformations of features you already have. And we know that any of these possible solutions could potentially make things better, or they could potentially make things worse. And we could, you might think, oh, I'll try all of them, but that gets very expensive. You cost money, your computing resources cost money, collecting data costs money. So you can't necessarily just try all of them. So as your machine learning expert, it's really important for you to understand how machine learning works in order to be able to use that knowledge for practical situations like this one. So it's not enough just to know how to, write the code to put the data into the model. You need to be able to understand what to do with the model after it's finished training and how to continue to improve it. Now, we already learned a few different ways for addressing, let's say, some potential problems with the model. So we have some idea of when we might pursue one or more of these attempts to improve the results. For example, we saw that you can use exploratory data analysis to try and identify problems or any assumptions you made about your data that are not accurate. And we also saw that if your model has good interpretability, meaning you can look at the model and understand what it's doing and why, that's also a good way to find problems with the data. Right? So last week, we started a linear regression case study that we didn't finish yet. We'll finish today. And in that case study, we looked at the coefficients from the model. So these are interpretable. They tell us which features have an effect on the target variable. And we were surprised to see that coefficients for features that were not expected to be useful were actually high. So that's an example of using the interpretability of a machine learning model to try and correct a problem with the data. So we saw a few kind of red flags that would tell us, okay, the next stop is find and correct the problem with the data. We also saw that there are some problems that can arise from model training, right? For example, when we looked at gradient descent last week, we saw that if you have collinear features, if your learning rate is too high, if your learning rate is too low, those are all examples of things that can lead to problems with the model training. We know that sometimes it's helpful to get more data to add features to each sample. This is something that you'll see in the homework from last week, but we also looked at it in the notebook from last week. We saw that we can look at residuals to see if there are some patterns in the data. And if there are patterns in the data, that can often be a signal that you need to add more features to the model, add interaction features to the model, sometimes add transformed versions of features you already have, so nonlinear versions of them. So we've already seen a lot of ways to kind of identify what the problem with the model might be and how to try and correct it in some cases. But in order to understand some of these other suggestions, so whether to change the model itself, use a more complicated model, less complicated model, whether we would benefit from more training samples, those are all things that in order to know how to do, we need to understand bias and variance. So that's what we're going to work on today. Okay, so we're going to start with a couple of illustrations. Let me pull up this table of contents. Okay, a couple of illustrations. First, we're going to think about polynomial data. So we know that we can represent some polynomial model using machine learning, using a linear basis function regression. This just goes through that. So we have this linear basis function regression which implements a polynomial model. So I have a function here that will generate that polynomial data. Okay. We can pass it a list of coefficients and an intercept, and it will generate data according to the polynomial with some additive noise. Okay, and now I'm going to go ahead and generate that data. Okay, so here's my data. It's generated according to this polynomial with the equation defined here. Now, in this case, I know the true function that generated the data, right? Because I created the data synthetically, I know the true function. Normally, we don't know the true function, but in this case, I do. So I'm going to go ahead and plot it. Okay, so this is a true function, and these are the data points. Why are the data points not exactly on the true function? Okay, so we have some noise. We always assume that data we have from the real world is not a perfect representation of any true function of x. There is some unmeasurable noise in it, not unmeasurable, unlearnable noise in it, and that's what we see here. Okay. Now, I'm going to use some transformed features derived from x. So I'm going to take x, okay, and then I'm going to compute, let's say, x to the power 1, x to the power 2, x to the power 3, x to the power 4, and I'll stack those all together. Sorry, it's actually only up to the power 3. Okay, so I'm going to stack these together. And let's see how we did. So the true coefficients here should be W0 equals 1, W1 equals 0.5, W2 equals 0, and W3 equals 2. So my fit is pretty good on this training data, and we can take a look at the fitted polynomial. So here, the red line is a true function, the green line is our model, and the blue points are our test points. How did our model do? Okay, so the model looks great. It's very close to the true function. Right? Here's a mean squared error. Now, generally, though, we don't really know the true model order. In this example, I generated synthetic data with a polynomial order 3, but I don't usually know what the true model, the true function looks like. So let's look at what happens if we were to try and fit a linear regression with just, d equals 1, meaning no higher order features. So I'm going to fit a linear regression just on x. Previously, I was fitting it on this matrix that was composed of these transformed columns from x. Now I'm fitting just on x. Okay. And here my green line is my model, my red line is a true function, and the blue line is the test points. How did I do? So this model does not do as well. The function that I use, that I assumed as a model class, which is the function, y hat equals w0 plus w1x, it's not able to capture the complexity of the relationship between x and y. You can see it's not flexible enough. So this is an example of underfitting. And this model has somewhat higher error. So this was the error of our previous model. This is the error of our new model. And here is the test error. Now, suppose we try to train a model order that's too high. So for example, d equals 10. So now I'm going to generate a new, let's say, transformed data set. Using that x column again, I'm going to compute an x to the 0 column, x to the 1 column, x to the 2 column, so on. And then I'll use it to fit the data. Okay, how does this look? So here the green line is my model of order 10. So in this example, it actually did pretty well. Right? So I happen to have gotten lucky. But let's compute the error. The test error here is, okay, so the training error here is 0.18. Let's look at the original model, so using the true one. For the true model, the training error was 0.19. And for the model with polynomial order 10, the training error is 0.18. Okay. So my training error is lower when I increase the complexity of the model. And as a general rule, it always will be. What about the test error? So for the original model, the test error was 0.178. Okay. For my polynomial model of degree 10, the test error was higher. So we see that when we increase the model complexity, your training error gets higher. Your training error will continue to decrease, but the test error starts to increase. Let's try using maybe a different polynomial order. Let's try using 20. Why not? Okay. So what does this model look like? If I compute the training error for this model, do you think it will be higher or lower than before? What will the training error look like? So the training error for the model with degree 10 was 0.18. If I compute it for this model with degree 19, I think it will be 0.16. Right? But what about the test error? Will the test error be lower or higher? So the test error before was 0.20. Change the number here too. Okay, now it's up to 0.22. So we can see that as we increase the model complexity, just undoing that, the training error will keep going down, but the test error will start to go up once we overshoot the complexity of the true function. This is overfitting. Because we're using a very flexible model, it's fitting the noise in the data and the particulars of the training data set, and not the underlying relationship, which is y equals t of x. Now, in this example, we know the true function. And when we know the true function, it's very easy to see the overfitting and underfitting. But in a real problem, we do not know the true function. If we knew the true function, we wouldn't need a machine learning model. So how do we go about determining the correct model order just using the data? So that is what we know as a model selection problem. And we know that one bad idea in order to do that is to just, let's say, loop over a series of model orders and measure the mean squared error on the training data for each model order, and then select the model order that minimizes that error. Right? So here's a loop. I'm setting up a, let's say, a blank matrix of zeros for saving the mean squared error of each model. And I'm making a list of model orders I want to test. Now I'm going to loop over those model orders I want to test and generate a transformed linear basis function data set for each one. So a design matrix for each one. Fit a model, and then I'll measure the mean squared error for that model. Okay, so I'm just looping over my potential model candidates and evaluating each model. So we know that as we increase the model complexity, the training error, which is shown in blue here, will always continue to decrease. So if you minimize the training error, you'll end up selecting this very high model complexity, which is an overfitted model. It has actually much higher test error. On the test data, we can see that at first, when the model complexity is less than the true function, over here, we have some bias, so there's higher test error. Then the test error goes down, but then it starts to increase again due to variance as the model complexity increases. Now, we don't necessarily want to just select the model based on the test set either. Right? So you might look at this and think, okay, I'm going to select this model with the best test performance. But we know that the performance depends on the random sample of data points that end up in your training and test set. When we're training, we kind of fit to that random sample, and we know that training error doesn't give us a good estimate of generalization error because we're fitting to that training sample. If we use a test error to do the model selection, well, then we're kind of fitting to that test sample too, because we're kind of tuning the model that we end up selecting towards whatever samples happen to be in the test set. So if we do that, the test set is no longer kind of independent and partitioned off from the model selection, the model training process. Then we're using the test set to train the model, and then we no longer have a clean test set on which to evaluate our model performance. So we don't want to do that. We don't want to use the test set to select the model either. Now, let's look at a different example of overfitting and underfitting. So besides for the polynomial example, so let's look at an example with many features that are not informative. And when I say not informative, I mean features that don't have any effect on the target variable y. So now I'm using a different version of this data generating function that I had previously presented. In this version, I have the option to select some informative features and non-informative features. Okay. The informative features are similar to the ones shown here. So they affect y. And then after I generate, let's say, a data set according to this, I'm just going to add some extra columns with extra x data in it. But those columns had nothing to do with y, right? So I generate y purely based on the informative columns. And then I generate some other random columns afterwards. Okay, so here's my data generating function. I'm going to generate some data with just a couple of informative features, 2 informative features, and 2 uninformative features. And they'll be in order. Okay. So looking at this data, the informative features are x1 and x2. The uninformative features are x3 and x4. Now, in this case, it's kind of pretty easy to eyeball it, and you can see that x1 and x2 are closely related to y, x3 and x4 are not. But we know that with more noise and with higher dimensionality, it becomes impossible to kind of just look at it and see. Okay. And if we fit a linear regression model, right, we could see like, okay, x1 and x2 have high coefficients. That means that an increase in, let's say, x1 of 1 causes an increase in y of about 5. Whereas for x3 and x4, we have very small coefficients, meaning their effect on y is close to 0. Is that good? Well, so if we have uninformative features in our data set, so features that have no effect on y, the true function, let's say, would have a 0 coefficient for those features. So we want a machine learning model to estimate a 0 coefficient for these 2 uninformative features. So in that sense, it's not too bad. This model estimated a coefficient that's pretty close to 0 for the 2 uninformative features, which is pretty close to reality. Now, what if we have many uninformative features? So now we're going to repeat this, but this time I'm going to have 95 features. 20 of them are informative. The first 20 features are informative features. That means that the data is the target variable y is a function of the first 20 features. The next 75 features are uninformative. That means y is not a function of the last 75 features. And now I'm going to fit a linear regression to that data. And I'm going to plot the coefficient values. Okay, so let's see what we have here. Okay, so remember that the first 20 features are the informative features. Let's kind of highlight those. So these are the informative features. Was the model able to correctly identify which features are informative and which ones are not? Okay, so we would expect that the informative features would have kind of higher coefficient values because they actually affect y. And the uninformative features ideally should all have coefficient value of 0, right? Because they don't affect y at all. But because there are so many uninformative features, and there is, as we know, noise in the data, there's this random relationship. You know, I say relationship, but it's not really a relationship, it's random, but it appears to be a relationship between the uninformative features and the target variable y. And that random relationship, again, not a real relationship, can actually look as strong or stronger than the true relationship between the informative variables and the target variable, right? So here we can see, for example, these are a couple of examples where informative feature was estimated to have a very small coefficient value, meaning the model thinks that it doesn't have any effect. And then we have many examples where the uninformative features have a large coefficient value. And here, we're concerned with magnitude, meaning the model thinks these coefficients have a strong effect. We know they should actually have 0 effect. What do you think will happen if we compute the training error and the test error? Okay, so the training error on this data is amazing, 0.99. Okay. But the test error is a whole other story. So the test error is a large negative number. Okay. This is an example of very severe overfitting. So the model does much worse on the test set than it did on the training set. Okay. Let's look at the reverse situation. So here, we're using a large number of features to train the model. Some of them are informative features, some of them are not, and we don't know in advance which are which. So we can see that our model has very severe overfitting because it does much worse on the test set than on the training set. So maybe we'll think, okay, I should use only a subset of the features then, because only some of these features are most informative about the target variable. But I don't know in advance which features are most informative. Okay, so we're going to try just randomly selecting one feature at a time and adding it to our model. And then we'll measure the mean squared error. Okay, so what do you think our training error is going to look like? Let's say if we build a model with one feature, then build a model with 2 features, then build a model with 3 features. What will our training error look like as we increase the number of features in our model? Let's drop. Okay, so I'm going to train many models with increasing number of features. And the training error is going to decrease as I increase the number of features in the model. Right? Is it because the model is doing a better job of predicting the true function? Okay, so to some extent it is, because as we add informative features, hopefully the model will do a better job of learning their effect. But also we're adding uninformative features, and the model is learning kind of these, what appear to be real relationships, but are really just random noise from the uninformative features. So the model is going to be overfitting to this. What do we expect to see for the test error? What will the test error look like as we, let's say, start with just one feature, then increase the number of features to 95? Okay, so Ben says a U-shaped graph. Do I expect it will start off higher or lower than D? Should I start off here? Sorry, higher or lower than the orange line? Should I start off here or here? So I expect that it might be a little higher than the training error, just because the model is going to be optimized for the training data. Okay, and I expect that, you know, maybe at times I'll add informative features, so the model error will decrease. But also sometimes I'll add uninformative features, and as I add uninformative features and have worse and worse overfitting, the test error is going to increase. Okay, so let's see if that's what actually happens. Okay, is this what we expected? This is R squared, it's not error. Here, let's make it error so that we can compare a little better. Is this what we expected? Okay, well, the training error looks very similar. The training error is blue over here, and in our plot it's orange. And we could see that as we expected, no, this is not showing. Sorry, this is now, yeah, mean squared. Okay, we can see that as we expected, the training error decreases as we increase the model order. So as we add uninformative features, the training error is going to continue to decrease because we're going to tune our model to that random noise. And we'll decrease the error, but only the training error. Now, as far as the test set goes, well, when we increase the model order, some of the times we're increasing the model order by adding an informative feature, and some of the times by adding an uninformative feature. So that's why this looks very bumpy. The order in which we add features in this particular feature selection, let's say method, is random. That's not a good method, but that's what we're doing here. So we're randomly adding features. Now, sometimes we add an informative feature, so our model error goes down. Sometimes we add an uninformative feature and our model error goes up. The specific pattern is going to depend on, let's say, the order we add features in. So if I rerun this, it might end up looking somewhat different. Okay, so this will depend on the specific order in which we're adding features. But the general trend is that as we add a lot of features, the test error is high. But as we add too few features, we don't get the minimum test error at the smallest number of features either. Why is that? So over here, we have a small number of features. We're not overfitting. Why is the test error high over there? So over here, we have some bias. So we have 20 informative features, but fewer than 20 features in our model. So we don't expect that the model can fully capture everything about the data because it's not using all of the informative features. Okay, are there any questions about this? So remember that we're trying to estimate some value y, which we know is related to x by some true function t of x, but also has some noise. So we don't have any data handy. That's an exact sample of, that's an exact feature of f of t of x. Sorry, that's an exact function of x. And we're trying to use the training samples to learn some function f of x w, which is parameters by some weights or some other parameters, such that the samples in the training set are approximately equal to f of w. Right? But we know that that's not our true goal. Our true goal is to learn the function that will approximate samples we have not seen yet. So samples from a test set, but that have been generated from the same distribution. And then the question is, what could possibly go wrong? So one thing that could go wrong is, as we saw above, maybe we'll try to learn a class of function that's not capable of expressing the true function. So we're going to have an assumed model class, an f of xw. And if the model class that we assume is not capable of expressing the true function, then we'll have some bias. It's a systematic difference between the true function and the model. We saw that in a couple of examples above. We saw that when we tried learning the third degree polynomial with a 1 degree line. And we also saw that when we tried learning, let's say, a relationship on 20 features, if we would use a smaller number of features. Right? So here, let's say we're trying to learn with a smaller number of features. So either of those situations will create bias in the model. Now, we also have situations where we might learn the right class of function, but because of the stochastic noise in the training samples and the random draw of training samples, we'll end up with an incorrect parameter estimate. Right? So for example, up here, when we estimate the parameter values, we know that they should in fact be 0 for, let's say, all of these, but they're not, because we're fitting to the noise in the training data. So that's what we call variance. We saw this in the polynomial example when we tried using a model with a degree higher than 3. So the complex polynomial is capable of expressing the true function. Right? We can express this t of x using f of xw. All we need to do is just set w equal to 0 for any, let's say, coefficient over 3. But we still had some error because our coefficient estimates are going to tune to the noise in the training data. And the more coefficients we learn, the more potential for error. So Ben asked in chat, is it a good idea for a model to use all the informative features? So the answer is, well, sometimes it is and sometimes it's not. It depends how much noise there is. Right? Even if there is, let's say, even if there is a feature that is, let's say, very informative, we still increase our risk of overfitting by adding more features. And we'll be able to see the extent to which we increase the variance term as a function of the number of parameters and the noise. So we'll see in a moment that sometimes it's helpful, sometimes it's not. Okay, so we saw this in a couple of places. So that was our variance. And then finally, we know that even if we have exactly the right function, so f of xw is equal to t of x, we'll still have some error because of the stochastic noise, and that's the irreducible error. Okay. So we know that we can take the overall mean squared error for a new test point and decompose it into the irreducible error, the bias, and the variance. And we know that the bias term captures the systematic difference between the function learned by our model and the true function. For example, when our model can't express a true function. And we know the variance describes the difference between the coefficient estimate due to a random training set and the average coefficient estimate. In other words, how sensitive is the model to the particular training set? Now, I put up these notes on Brightspace. Which goes through the process of deriving the bias and variance for the linear regression specifically. And we ended off with a few high-level conclusions. Let's just look at that. What are the high-level conclusions? Well, one is that if there is no under-modeling, meaning if you have a assumed model class that's capable of expressing the true function, then the linear regression estimate of the ordinary least squares estimate of the target variable is unbiased. Okay. What does that mean? It means that for the linear regression using the least squares estimate of coefficients, the bias term here is going to be 0. That's assuming there's no under-modeling. Okay. Then we also saw that the variance of the estimate of the target variable depends on 3 factors. It just depends on the number of features, it depends on the number of training samples, and it depends on the noise. Okay. So the variance increases with the number of training parameters, increases with the noise, and decreases with the number of samples. So to answer your question, Ben, it will really depend on how many training samples and how noisy you are, how noisy the data is. So we know that increasing the number of features, even informative features, will always increase the variance, right? And it will increase the variance by an amount equal to sigma epsilon squared over n. So adding one feature will increase the variance term by the noise variance over the number of samples. On the other hand, omitting an informative feature will increase the bias. So if you, let's say, omit an informative feature, then you increase the first term, but you decrease the second term. So that trade-off will depend on, let's say, how many training samples you have, how much noise is in the training samples, and of course, it will also depend on how much bias is attributed to that particular feature. Okay, so we have these overall conclusions. Take a look at that and remember that. Now, we're going to do a series of simulations. In the following simulations, we're going to look at pairs of regression models. And for each pair, I'm going to ask you which model in the pair will have more bias, which model in the pair will have more variance. Okay. Then we're going to check our answer by doing a simulation. In our simulation, we're going to draw a test set. We're going to put the test set aside. Then we're going to do many experiments in which we draw a training set, fit a model, and compute the error in the test set. So we're going to have one test set, many training sets, and we're going to train many models for each, let's say, model class we consider. And then we'll look at the overall effect. Now, I have 2 important notes here. One note is that we cannot do this in general when using machine learning on a real problem. Why not? Is it generally possible to just like have many, many training sets and keep training on more and more training sets? Okay. So the problem is that usually when you're solving a real machine learning problem, you're not generating the data yourself, right? You have a finite amount of data and you need to train a model using your finite amount of data. What we're about to do, the simulation we're about to do, basically assumes we have an infinite amount of training data. So we can keep sampling from the training population over and over and over and over and never run out of training data. Of course, in real life, we can never do that because we only have a finite amount of data. Now, also this procedure we're about to do will give us an approximate bias and variance, but it's not going to be the exact bias and variance that we would compute using these expressions. Why not? Okay, so these expressions are computed as a expectation over an infinite, basically an infinite sample of test points, an infinite number of draws of training samples. So it's basically an expectation over infinity, right? Which of course we're not going to do. We're going to have a finite number of experiments. And so our examples won't give us the exact bias and variance, but will give us a good idea. Okay, so let's start. And we're going to guess each thing here. Okay. So before we run each simulation, we're going to try and use our understanding of bias and variance to identify what the bias and variance of these models will look like. Okay. So here we're going to start with two models. Model A is a constant model, so we're going to predict 1 for every sample. And model B is going to be a prediction by mean. So we're going to predict the mean of the training samples. Okay. And the data is generated as y equals 1 plus epsilon. I'm going to ask you about the variance and the bias of these models. And I want you to think about two things. When you think about the bias, okay, I want you to think about what would the mean of each model look like? And is the mean of each model different from the true function? Okay, so that's a part of the y that's a true function. So when you think about the bias, think about whether the mean of the model is going to be different from the true function, or which model will be more different from the true function. And when I say think about the mean, I mean the mean over an infinite number of experiments. And then when I ask you to think about the variance, I want you to think about how different each individual model will be from the mean model. Okay, so let's go ahead and let me know which model you think has more bias or more variance. Okay, take about 5 more seconds to vote. Okay, so let's see what you all thought. Let's start by thinking about the bias of these models. Okay, the true function is y equals 1. What's going to be the average model for model A? Okay, so the average model for model A is y equals 1. So the average model model A is exactly equal to the true function, okay, which means this term, which computes the difference between the true function and the average function, will be 0 for model A. Okay. So when the true function is exactly equal to the model mean, we have an unbiased estimate. So model A has zero bias. What about model B? What's the mean? What does a mean model look like for model B? So the data is generated from y equals 1 plus epsilon, where epsilon is zero mean. So the mean of epsilon is zero, which means that the mean of model y of model B will also be y equals 1. Okay. So again, looking at this bias term, for model A, the true function is equal to the mean function. For model B, the true function is also equal to the mean function. Okay. So for both model A and model B, the bias will be zero. So the bias of model A and model B is the same at zero. Okay, what is a variance of these models? So the variance tells us how different each individual model, so we're gonna, let's say, sample a bunch of models, each trained on a different training set. And we're interested in knowing how much each individual model will vary around the mean model. Okay. So both of these have the same mean model. Does model A have any variance at all? Model A has no variance. So every single individual model I sample is going to be y equals 1. So every model will be identical to the mean model. What about model B? So the mean model for model B is y equals 1. But depending on the random draw of training samples, I'll sometimes get slightly different values. So let's say one model might be y equals 1.105. Another model might be y equals 0.98. So we expect to see some variance here. So model A and model B both should have zero bias, but I expect that model B will have higher variance. Let's see if we're right. So we're going to actually generate some test data. Then we're going to simulate training many times on different data and compute our error. So we're going to draw all the individual models and the mean model and the true function. Okay, so here's model A, the constant model. Okay, the red solid line shows the mean of our models, and the blue points are our test data. Okay, does model A have any bias? So remember, the true function is y equals 1. Is the mean of model A equal to the true function? Okay, so model A, the mean is exactly equal to the true function. Also, model A, we have no variance. So each of the individual models that we trained from random training samples are exactly equal to the mean. What about model B? Okay. So model B, each of those orange lines shows one instance of the model trained on a random training sample. So we could see every time we train the model on a different training sample, it's slightly different, but on average, the mean of the model is y equals 1. So both of these models have no bias. They both approximate the true function correctly, but model B has more variance. Now, what we're looking at here is the decomposition of error for each individual test point. Okay. So imagine, let's say, this test point over here. Okay. Or let's actually take this test point here. Okay. So this test point has some error. Okay. This is a total squared error averaged across all of the instances of this model. Okay. And we could see the contribution to the total squared error from the bias variance and irreducible error. It's a little hard to see because in this case, the irreducible error is overlapping with total squared error completely, meaning the only error term here is the irreducible error. So there is zero bias, zero variance. In model A, there is no variance because there is nothing random about this model, right? It's a constant model, which means that when we look at the variance tells us, let's draw this. The variance tells us the difference between, let's say, each individual model. Okay, so let's say I'm training model fit 1, model fit 2, model fit 3, and so on. So what's the difference between model fit 1 and the mean model? Well, it's 0 because model fit 1 will be y equals 1. Mean model is y equals 1, 2. What's the difference between model fit 2 and the mean model? Also 0. Right? Between model 3 and the mean model, 0 again. So for the constant model, there's no variance because every time I fit the model, it's going to be exactly the same as the mean of all times fitting the model. Now let's look at this plot over here. So for model B, we see slightly higher error overall. The irreducible error is the same. The bias is also 0. Now here it's like, some very small number. Remember, we said that we don't have an infinite number of experiments here. So we're not exactly getting to the correct bias. But if we had an infinite number of experiments, I would expect this bias term to go to 0. Variance, on the other hand, is not 0. Right? The variance is not 0 because each individual model, which is each of these individual orange lines, is different from the mean model. Right? So when the individual models vary around the mean model, that's variance. And that tells us how sensitive is the model to the training data. If you get a different model every time, depending on your random sample of training data, then your model is sensitive to the training data and has higher variance. Okay, let's try a few other things. So what do you think would happen if we used y hat equals 2 for the constant model instead of y hat equals 1? Okay, so here are a constant model of y hat equals 1. What if we made that y hat equals 2? I'm going to start plotting it so that we don't have to wait. Let's try this. So now my constant model is y hat equals 2. Remember, for the bias, think about the difference between the true function, which is y equals 1, and the mean model. And for the variance, think about, let's say, which model will have more variance around the mean model for individual models. Okay, take 10 more seconds to vote. Okay, so here we think that model A has higher bias. I agree with you. The true model is y equals 1. The mean of model A will be y hat equals 2, which has some bias because it's not equal to the true model. The mean model for model B will be y hat equals 1, which has no bias. So I believe that model A will have higher bias. Model B will continue to have higher variance. So for model A, there is no variance of individual models around the mean model. The mean model for model A is y hat equals 2. Every individual model is also y hat equals 2. So there won't be any variance. For model B, there's some variance because the mean is slightly different every time depending on the draw of our training samples. Okay, so let's take a look at this. It looks like I did not update the plot correctly. Let's see. Oh yeah, I didn't do that correctly at all. Okay, so now my model A is going to be to predict a 2 always. And we'll repeat this. Okay, while we wait for that to finish plotting, let's think about some other things here. So what would happen if for the mean model, instead of using y equals y bar, we used y equals y bar plus 2? What would happen then? If we used y equals y bar plus 2 instead of y equals y bar, would we increase the bias of the model? Okay, so in that case, we would increase the bias of the model because the mean model would be different from the true model by 2. But we wouldn't necessarily increase the variance because the variance won't have any, this constant term won't have any effect on the variance. All right, let's look at our plot now of our model A, which is a constant model of y equals 2, and our model B, which is the mean model. So now we can see some bias in model A, right? The true function is y equals 1, but the mean of model A is different from the true function. Model B still has no bias. And when we look at the total squared error, so we could see for each individual point, the total squared error includes the bias, which is this horizontal blue line here. So there's a constant squared bias for every single individual point. Then we also have no variance here. And finally, we have some irreducible error that's shown in purple. Okay, let's try another example. So now we're going to imagine that data is again generated as y equals 1 plus epsilon. And we're going to consider two models. One model where y hat is a linear model with d equals 1, and it's trained using least squares. And model B is our mean model again. So which model has more bias and which model has more variance? Okay, and remember, when you're thinking about the bias, think about what the mean of each model will be and compare that to the true function, which is y equals 1. And when you're thinking about the variance, think about how sensitive the model is to the training data and how different each individual model might be from the mean model. Take a few more seconds to vote. Okay, let's think about these results because I agree with some of your votes and disagree with some others. What will be the mean model for model A? What do we think will be the mean parameter estimates for model A? So I would imagine that for model A, if we would train model A many, many times on different training samples and then average all those trained models out, I would imagine that the average parameter estimates will be y0 equals 1 and y1 equals 0, because that's what will best fit the training data. So on average, I expect model A to be y hat equals 1. Does y hat equals 1 have any bias? Okay, so for this data, no, because y equals 1 is a true function. So model A is unbiased. What about model B? Model B is the mean of the training samples. What is the mean of model B going to be? Okay, very good. So the mean of model B is also y hat equals 1. If I give model B many training samples generated by this process and compute the mean, I expect it to, on average, come up with model y hat equals 1. So both of these models have 0 bias. I expect them to have the same bias, and they should both have 0 bias. That means that the mean model should be the same as a true function. Now, what about variance? Which model do we think will have higher variance than y? So notice that model B is essentially this model. So model B is essentially y hat equals W0, where if you compute W0 using the least squares method, you're going to get the mean of y. And model A is W0 plus W1x. Which model has more parameters? Okay, so model A has more parameters. And remember, we said that for a linear regression, the variance increases with the number of parameters if the data is noisy. So if sigma is greater than 0, then the variance will increase in proportion to d. So here I expect that the model with d equals 0, essentially, will be less varied than the model with d equals 1. Let's try it out. So what do we see here? First, let's look at bias. Does either model have any bias? Okay, so both of these models are unbiased. For both models, the mean of the models, which is the red line, is y equals 1. And you can see here also when we look at the individual error for each individual point, again, the bias is essentially 0. I mean, we don't have infinite number of experiments, but the bias is going to 0 with increasing experiments. What about the variance? So the variance is represented by how spread out the orange lines are around the mean model. Each orange line represents a different model fit on a different random training sample. And so for variance, we're looking at how spread out it is around the mean. In which model is the orange lines more spread out around the red line? So we can kind of visually see that for model A, which is the more complex model, the orange lines are much more spread out around the red line than the blue lines. Especially in the corners, you can see the orange lines sometimes end up all the way over here. Whereas in model B, the orange lines are pretty close around the red line. So model A has more variance. This tells us that if you train model A many times on different training samples, well, let's draw over some of these individual lines. Sometimes you'll get this, sometimes you'll get this, sometimes you'll get this, sometimes you'll get this line. On average, you'll get the correct line if you would train such a model many times on an infinite population of data. But the individual lines you get actually vary a lot around the mean. Okay, are there any questions on that? Let's look at another example. So in this example, I'm not even going to tell you how the data is generated because it doesn't matter. But in this example, model A and model B are both a linear model with one feature. But model A is trained on 10 training samples and model B is trained on 1,000 training samples. Okay. Which model will have more bias and which model will have more variance? So remember, when thinking about bias, think about what the mean of each model will look like relative to the true function, which you don't know in this case. And when thinking about variance, think about how sensitive the model will be to the training sample. Okay, take a few more seconds to vote. Okay, let's think about the bias of these models first. Is the average model A going to be any different than the average model B? I would say that the average models is not going to be different. So the average model is what would we get if we trained a model infinitely many times over many training samples? I expect that on average, the average model will be the same for model A and model B. Right? So I expect both of these models to have the same bias. If this expression does not capture the true function, then there will be bias. If the true function is captured by this expression, then there's no bias. But I would expect the average model to be the same for both. Okay, what about the variance? Which model do I think will have, let's say, more variance in the individual model relative to the mean model? Okay, so I see a small majority said model A has more variance. Why? Okay, so if you think about it, it's kind of intuitive. that if, let's say, if you have a small number of training samples, well, you might get a line like this. If maybe on the next example of training your data, you have these training samples, you might get a line like this. Right? So it's easy to see that with a small number of training samples, you could potentially get wildly different models every time. But if you have a large number of training samples, then you would expect every time you train your model to be kind of similar. And this is consistent with the analytical results that we shared. Just clear that. So this is consistent with the analytical result we shared here, which says that the variance decreases with the number of samples used for training. So let's see if that was true. Okay, so here's model A and model B. Now in this case, the true function is linear. So both of these models are essentially unbiased. Now you might see like a small bias term here, but again, that's just because we don't have an infinite number of experiments. Okay, the stochastic noise is the same for both models because that's independent of the model. It's just about the data. And then we have the variance. For which model is there more variance around the mean model? Okay, so clearly for model A, the individual instances of models trained on 10 samples of training data vary more than the instances of the training models, the instances of the models trained on 1,000 samples. Okay. So the more data we have for training, the less variance we have in our model. Let's try one more example. Okay, so here my data is generated according to this function. And model A is a linear model on one feature. Model B is a polynomial that goes up to degree 3. Okay, go ahead and vote. Okay, so remember, when thinking about the bias, think about what the mean of each model will be. And when thinking about the variance, think about how much the individual trained models would vary relative to the mean model. Okay, take a few more seconds to vote. Okay, so this time we said that we think model A will have higher bias. Let's look at the mean models again. So for model A, we can see there's a systematic difference between the true function and model A. Epsilon term doesn't really matter because it's zero mean, so it will go away on average. But as far as the mean model goes, right, there is a term in the true function that cannot be represented in model A. That will create a systematic difference between the true function and the mean of model A. So I would expect model A to have some bias because of this term here. What about model B? Okay, so again, this term will go away. On average, I expect model B to, let's say, end up with W0 equals 1, W1 equals 0.5, W2 equals 0, and W3 equals 2. So on average, model B could be exactly equal to the true function. So my expectation here is that model A will have some bias and model B will be unbiased. Let's run it so we don't have to wait. All right, let's think about variance. Which model has more variance than Y? So I think the majority said model B has more variance. Why? Why does model B have more variance? Okay, so Greg is correct. Model B has more parameters and the variance increases with the number of parameters. Now, I have a question for you. Is there a model that has less bias than model A, but less variance than model B? What would that model be? What if I had this model? Would this model have less bias than model A? Okay, so remember that the bias of model A is due to not modeling this term, which we have here, so that's fine. Does it have less variance than model B? So model B, we have 4 parameters. In this new model here, we have only 3 parameters, the 3 weights to estimate. So this model would have less bias than model A, but less variance than model B. Okay, let's take a look and see how model A and model B did. Okay, first let's look at the mean model. Okay, remember that the true function looks like this. In which, do you think there's a difference between the true function and the mean model for model A? Okay, so it's pretty small, but if you look at this bias term here, you look at the 0.08 compared to the bias term here, which is much closer to 0. You could see that model B is essentially unbiased. With an infinite number of experiments, I would expect it to go to 0. But model A has some small bias due to that 2x cubed term, which is not represented in model A. What about variance? So which model has more variation around the red line of the orange lines? So model B has more variation. You could see, especially at the edges, in model B, the orange lines might go all the way up here. Whereas in the model A, They're more closely clustered around the red line. Let's see what happens if we decrease the noise here. I'm going to decrease the noise. Do I expect the bias to be affected when I decrease the noise? Okay, so the noise should average out. It shouldn't affect the bias. How do I think the noise will affect the variance? Okay, so the noise will decrease the variance of both models, because remember, the variance is due to the random draw of noisy training samples. And with less noise in the training samples, I expect the variance to decrease. Okay, so Wei asked, does noise and variance mean the same? So that's a very good question. The answer is no. Right? So we have noise that's, let's say, part of how the data is generated. Right? So the data is generated with this epsilon noise, and the epsilon has variance sigma squared. Right? So in our final error decomposition, we have some error that's just from the noise entirely, right? So sigma squared. So that sigma squared is directly due to the noise. Then we also have a bias and a variance term. The bias term is due to the difference between the mean model and the true function. And the variance term is due to the difference between individual models and the mean model. Now, the variance term depends on the noise, because if there is no noise at all, then there is nothing very random about this. And I would expect that the training samples will give us the same coefficient estimates every time. So the variance is definitely affected by noise. And we can see here that the variance is proportional to the noise for the linear regression particularly. But noise and variance are not the same thing here. And for other types of models, the relationship between variance and noise might not be exactly like this. That's a good question. Okay, so here we can see we reran this with less noise, and the variance for both model A and model B has decreased. Okay, so I hope that kind of clarifies this concept of bias and variance of linear models a little bit. And you can feel free to play around with this notebook and change the parameters yourself as you look at this later. Now, we know that depending on our model complexity, our model might have high bias, high variance, or somewhere in the middle. And then the challenge is how to select the model. And we said in class that instead of just dividing our data into training and test, for model selection, if we want to evaluate different model candidates, we would divide our data into training, validation, and test. So use training data to train the model for different candidates, use validation data to select the model, and then use the test data to evaluate the performance of the model on brand new data. And then we also said to reduce the dependence on the particular samples chosen for training, we can use k-fold cross-validation, where we divide the training data into k-folds, and then we'll run our training and validation many times, k times, where for each time a different fold will be used for the validation set. So this helps us reduce the dependence on what samples happen to end up in the training data versus validation data. So let's try this example now. So we're going to generate some polynomial data similar to our first example with degree 3. And we're going to divide our data into a training and a test set. Now, when we do k-fold cross-validation, we'll further divide the training data into training and validation. But for now, we'll just have training and test. And now I'm going to use k-fold cross-validation to, let's say, select the optimal model order. So we're going to have two loops. In one of our loops, we're going to loop over these folds. So here I selected k equals 10. And then I'm going to use the scikit-learn k-fold function to create folds out of that data. Okay. And I'm going to use this, let's say, kf split to split the data. Now, when I split the data, it's going to return. Okay. When I split the data, it's going to return a pair of arrays, where the first array will be the indices of all the data that should be in the training set for this fold. And the second array is the indices of all the data that should be in the validation set for this fold. So I'm going to get the indices for the training data and indices for the validation data for this fold from the k-fold object. And then I'll prepare my training and validation set using those indices. So I have the indices of the training set and the indices of the validation set. Now that I have my data, I need another loop. So now I'm going to loop over all my candidate models. Over here, I created a list of candidate models, which are just different degrees of polynomials. And now I'm going to loop over all the candidate models. And for each candidate model, okay, I'm going to prepare the linear basis function regression for that candidate model. I'll train it on the training data. And then I'm going to measure the mean squared error on the validation data for this fold. So this outer loop, I'm going to go through k times, so 10 times because I'm doing 10-fold validation. And I'll go through the inner loop nd times, so as many times as your model candidates. Okay, let's try it out. Okay, so here I'm plotting the mean squared error across all 10 folds for each model candidate. So this is the mean squared error for model candidate 1 with model order 1. This is a mean squared error for model candidate 2, and so on. Okay, now remember, this is following example from the very beginning, right? So if the true model order is 3. So this is actually very consistent with my expectations that the validation error is lowest for the true model order. Okay. So in this case, actually, the model order that gave us the lowest mean squared error was actually model order 4. So if you would use a NP argmin function, this argmin function tells us, okay, in this array, so the array is MSE val mean across axis 1. Let's actually look at this. So this is MSE val. Okay, so you could see each, let's say, subarray here has 10 values, which is, let's say, the values for each of the individual folds. So then I'll take the mean across axis 1. Okay. And now I get the mean for each individual model order. Then I'm going to find the index of the entry that has the lowest mean, okay, and that's 3. And then I'm going to use that index inside my list of model candidates to find out what is the model order that has the lowest mean squared error. So it turned out that the model order 4 had the lowest mean squared error here. Now I'm going to plot it with a, let's say, optimal model according to the best k-fold cross-validation score. Now you could also do this with R2. So here I was selecting according to lowest mean squared error. I could also select according to highest R squared, and the idea is the same. Now we said that when using k-fold CV, you sometimes select an overly complex model. And that's what we saw here. We know that the true optimal model, the true function is a polynomial of degree 3. But when using the k-fold cross-validation, we selected an overly complex model. And that's because we're still kind of like fitting a little bit to the validation set. So there's a little bit of overfitting going on. So we said, as an alternative procedure, well, we can still find the optimal model according to the best k-fold cross-validation score. But then we'll find the simplest model that's within 1 squared error of that optimal model. Okay, so here, again, selecting the model that's the best according to the cross-validation score. Then for my target, I'm going to compute the mean squared error for that model and add that to the score of the model. And then I'm going to use the NP-WIR function to find a list of all of the models where the mean squared error is less than 1 standard error plus the mean of the optimal model. Okay, it's a lot easier to explain with a plot. So let's look at that. So here I had my mean and my standard error for each model. Now you remember that the model that had the lowest mean squared error was model order 4. Okay, so that's here. I'm going to draw a line that's 1 standard error above the mean error for model 4. And then I'm going to find the simplest model where the error is less than that line. And that turns out to be model 3. What if I was using R squared instead? So that's a higher is better metric. Okay, so here I'll do a similar thing, but I'm going to reverse all of the maxes and pluses and minuses. So now I'm going to find what is the model with the highest R squared. Then I'll compute the target that's 1 standard error less than that. And then I'm going to find what is the simplest model that has an R squared greater than the target. And that again turns out to be model 3. Okay, are there any questions about anything in this notebook? In your homework this week, you'll be doing some model selection, and you can feel free to reuse this code in your homework notebook. All right, if there are no questions, there's a question. So why is transformation of features to create new features not duplicating data? So when we talk about duplicating data, we mean duplicating data rows, right? So creating multiple rows that have the same data in them. When we're transforming features to create new features, we're creating more columns. So this is like kind of expanding the feature space for each row, but we're not adding more rows. So it's not considered duplicating data in the same sense.